Okay, just to recap what we did in class today, Monday, August 29th, for bell work, because there's two molecules that you'll have to know how to draw in a Cambridge exam. One being sodium chloride, which we haven't done in class yet. We'll do tomorrow, Tuesday. The other one, water. So we practiced doing the water molecules to show the electron sharing present in the atoms, and I said do this 3 times. Okay, so just after the first couple of classes that I had, couple things that we'll probably need to just keep some tabs on, keep note of. This is the best way to do it, and that's just my opinion based off looking on the Cambridge mark scheme, the answer key. Let's make sure that we're labeling them first. They weren't labeled, and so I don't know if that would be counted as correct. Okay, oxygen is in group 6 of the periodic table, so it has 6 valence electrons. 1, 2, 3, 4, 5, and 6. Okay, so we know oxygen needs 2 more to be stable. And what stable means, that it has a full outer shell. And then hydrogen, each comes with its own. Here's hydrogen, here's hydrogen. Hydrogen has 1 valence electron, and then we have 2 hydrogens there. So it has its own valence electron, and then it needs 1 more because it only is in the first orbital. So the first orbital can only hold 2. Okay, and then what's important is that we're showing like this area right here, right? So you can't, this is what we want to show the sharing of electrons with. On a Cambridge exam, we can't use color or anything like that. But by, making like a Venn diagram like shape, you could definitely be able to get this done. So oxygen, hydrogen, hydrogen. All right, we know literally like after doing this multiple times and after doing it on this one as well, right, where we've already done it in separate colors and then we've shown where they're going to be needing to share. At this point, like you could really just consider hydrogen needs 2 electrons to be full, oxygen needs 8. We're going to have 8 around that outer shell. 1, 2, 3, 4, 5, 6, 7, 8. So we can place 8 electrons around oxygen. We just need to make sure that we're getting them right here as well. This is the most important part to get those marks. Where one of these electrons are coming from hydrogen, and then the other one's coming from oxygen. So there's 4 total there, 5, 6, 7, 8. And so this is going to be what you'll have to do on a Cambridge exam potentially if you're asked to have to do that. All right, then we did it a 3rd time. Okay, and then in class we went over these ones too. What type of bond does water have? It has a covalent bond. And this is actually just a recap of the exam question that we did on Thursday. Why do hydrogen and oxygen form bonds, or why do they assist each other with electrons? It's to have full outer shells. Not just full outer shell, there's more than one atom, so we're going to say shells. Be careful with saying anything about 8 valence electrons or the octet rule, because hydrogen cannot hold 8, hydrogen can only hold 2. So instead of having to write your way through and explaining that, we can just say full outer shells. How many valence electrons does hydrogen have? It has 1. How many more does it need? It needs 1 more. How many valence electrons does oxygen have? 6. How many more does it need to have a full outer shell? 2. How many hydrogen atoms are required for each oxygen atom? It is H2O, so we do need 2 hydrogens for each oxygen. Otherwise, it would be this, which is hydroxide, which is what bases, not acids, but bases typically have. And they're extremely volatile anyway. But even if it was, if oxygen has 6, hydrogen has 1, it only puts you at 7, and we want to have 8 for the oxygen. Okay, electrons are shared between the hydrogen and oxygen atoms. So in the space below, I said draw 1 more large molecule of water. Great. oxygen, hydrogen, hydrogen. And I'm going to use red to show my electrons. 2 here, 2 here. All right, one of them in each little sharing area is coming from hydrogen. The other one's coming from oxygen. I knew oxygen came with 6, so there's one. Yikes. There's that 1, 2, 3, 4, 5, and 6. But total now, oxygen has 8, hydrogen has 2 apiece. Great. All right. So which atom holds more electrons? It's going to be oxygen. This causes the, and you could say, you literally could have started this sentence here, I, with hydrogen or oxygen, but this causes the oxygen atom to be partially negative, while the hydrogen atom is partially positive, right? So oxygen has, comes with 6 electrons, but it's having 8 orbiting its outer orbital, while hydrogen each comes with 1 electron, and at any time there's 2 orbiting its outer orbital. And they're not going necessarily just like in a clockwise formation. It's nothing like that. They're like everywhere, like orbiting everywhere, all over that electron cloud. What a big mess. I'll get rid of it. All right. Okay. So we would say then that oxygen is partially negative, and there's that fancy uppercase delta, looks like that, while the hydrogens are partially positive. Comparatively, there's just more negativity surrounding the oxygen atom, right? And this is what makes them have an unequal sharing of electrons. They're not shared equally. Hydrogen can only hold 2 max, while oxygen can hold 8. This does not mean it's ionic, because they were sharing electrons. They did not transfer electrons. Okay, so then that was the bell work, and then it's going to bring us to our main lesson today, which was hydrogen bonding. Comes from these parts of your notes. Okay, and then you had explained the formation of hydrogen bonds in water. It is a weak bond, and it can bond to oxygen, nitrogen, or fluorine, but we're looking at oxygen, always oxygen. Okay, oxygen can hold more electrons on its outer shell, and this is causing it to be partially more negative. Okay, therefore electrons are shared unequally. The partially negative oxygen atom will attract a partially positive hydrogen atom because opposites attract. So in my notes, it kind of looks like that. Again, this uppercase, is it? Oh, my bad. It is lowercase. Uppercase looks like that. That we use for change in. But lowercase delta means partial charge. All right, and though it is a weak molecule, it is a weak bond. The hydrogen bonds that cause water to be attracted to itself is weak. But if you do like a cannonball in a pool or you're splashing water around, it still pretty much comes back to itself. Or even just like a drop of water next to a drop of water will make a bigger drop of water. The reason for that is because in one drop, just one drop of water, you have 1.5 sextillion water molecules. So there's constantly going to be something for them to attract to. And this allows those really good properties of water, so that it is a solvent, right? Because it does have the opposite charges. So it can dissolve other things that have opposite charges or polar, that are polar. It can also dissolve things that are, sorry, I just don't like the size of that. Just bear with me. There we go. Can also dissolve ionic bonds, because ionic bonds have unequal like charges. Your metals are giving electrons away while the nonmetals are taking it. In terms of density, the fact that it's solid can float when it's in its liquid. And then specific heat. There's so many bonds that it can really hold its temperature really well. It takes a lot of energy to break that, to change that temperature, start to break those bonds. And so this will come to the new term we're going to give for water molecules. Okay. So recall from your vocab that the definition of polar, and your vocab quiz, a lot of people mix polar with ionic, but polar is when you have opposite sides of a molecule. Molecules are formed when you have 2 nonmetals or through covalent bonds when they're sharing. But when a molecule has contrasting charges, Okay, an example of this, like we know that water can dissolve sugar, so glucose. If water can dissolve it, then we know that glucose is also a polar molecule. Things that are nonpolar would be oil, fats. Water cannot dissolve that. There's nothing for it to attract to. All right, I did briefly show this video in class. It's 2 minutes, 47 seconds, and you can click it by opening up the Google Slides. All right, and so on the practice paper that we did, it said water is formed through covalent bonds. So we're just talking about one water molecule here. Due to unequal sharing of electrons, water is described as being polar, meaning it shares electrons unequally. Therefore, we will call it a polar covalent bond. Right, and that's something that we are going to have to be able to term it correctly on Cambridge exam questions, which is why I bolded it. It's a polar covalent bond. Water molecules are attracted to themselves through polar covalent bonds. Water, just one molecule of water, just one molecule, just one, is formed through covalent bonds. But then why does it attract to itself? That's because it's polar covalent. Covalent meaning that it's sharing electrons, and then polar meaning that it's sharing unequally. So I said below, use the molecules, add more if needed to show the unequal sharing of electrons and how other water molecules will be attracted to it through hydrogen bonding. So this is bonding on your hydrogen atom. This is why water is cohesive. So I'm gonna throw on 2 more water molecules. And then I'm going to use red to show negativity. So where there is going to be a partial negative charge, and then I'll use blue to show partial positive charges. All right, we know that oxygen is holding on to more electrons. Therefore, oxygen is going to be a little bit more negative, a little more electronegative. Right. Way to go, parrot. All right. Okay, I did all the oxygens. I did. Now I'm going to do the same thing with my hydrogens. I'll also post a blank copy of this on the Google Classroom so you can have that. So you can do this too and have it ready for whenever you come into class. Practice with the video. All right. And so other things I compared it to, right? Like you have the North Pole, the South Pole, so opposite ends, but also magnets, right? So opposite ends of a magnet will attract to themselves. The same sides, no, they will not. They'll repel. And that's why in our water molecules, opposite ends of the water molecule will attract to other water molecules. And so I'm going to show the electron sharing, I don't know, I'll use the blue, whatever. Okay. No, I didn't mean to say electron sharing, the hydrogen bond attraction. So it'll look like this. Right, the positive end of hydrogen is attracted to the negative end of the oxygens. right. And now that this is a weak bond, so it's easy to break, right? It's not like jumping into concrete unless you're really high away from water. But you can, do a cannonball in the water and it'll splash around, but then still kind of come back and take its water shape. Adding in heat, right? Adding in kinetic energy, that will break it. Adding heat or adding energy to particle movements, increases particle movement and it causes bonds to break. So like in liquid water, those hydrogen bonds, yes, they are weak bonds, but there's a lot of them. So they're constantly rejoining themselves. It does not take much energy to cause water to start to evaporate. I think it'll evaporate around like 68 degrees or 60 some degrees Fahrenheit. I'm going to look it up right now. Give me 1 second. Just have to know. What temp does water evaporate? So it boils at 212 degrees Fahrenheit, but can we go to evaporate? Cool. And an answer is not readily given. Okay, we know it's low, right? Because we live in Florida and we know that like we'll lose water just through evaporation. That could also be through wind as well. But those bonds are always constantly regaining themselves. Why could I get that answer so fast? Way to go, internet. Anyways, if we consider gas, obviously it's a vapor. If this is water, like there's no formation, there's no bonding. I should rather say instead, there's no bonding. Like they're too far away. There's too much energy to break those bonds. They're random. There is no hydrogen bonds. In liquid, there are hydrogen bonds holding water together, but in a solid, those hydrogen bonds are actually really strong. I wonder if this will play. Okay, it's not. So like one way that I describe this is, why ice will float. Well, in any given water volume, right, or water amount, okay, in a liquid, right, there is attraction that holds them together. And they have a more kinetic energy. Kinetic energy is heat energy, and that makes them move. All right. Increasing the heat on something can break its bonds, cause it to change its state, basic stuff. Okay. In a liquid. That's not fair. Sorry, that was on the actual slides. Okay. Well, if I remove heat, right, this will have like high kinetic energy, which equals particle motion. And they're moving so much, they're able to like defy these bonds that are trying to hold them in place. And they can't, but they're easily going to reform. But in ice, right, when it's solid, also going back to the liquid, you can have way more water molecules than in ice because they're almost like they're defying this. Like they're not following necessarily that hydrogen bond because it's so easy to break. You can smash so many water molecules in there. Plus, in a liquid, from like physical science, chemistry, but physical science, just basic. In a liquid, you have a little bit more heat, a little bit more energy. There's no definite shape to them, but they do have to take like whatever volume they're in. But those particles are moving. They're moving even faster from each other, breaking those bonds even more whenever you add even more heat and it causes them to evaporate. But in a solid, notice they have a definite shape. They're staying in that shape. Okay, and I'm almost done. All right. All right, so in the same amount, like in the same space of water, and this is why we also say that water expands when it's frozen or ice expands. Really, instead of we can think expands, they're like following the rules. If we think back to like during lockdown and COVID and quarantining, maintaining 6 feet, right? Prior to that, you can smash a lot more people in an area, right? You could have so many more people there, but then now we have to follow these certain rules where now there has to be 6 feet apart for people. Only a certain amount of people allowed in a certain amount of time. Not every single seat at a restaurant could be full. You're going to have to seat every other seat. Things like that. You couldn't fit as many people following those rules. But now, like, in a liquid, they don't follow those rules. In a liquid water molecule, these are weak bonds. They're able to break them. These bonds right here, they are able to be broken, and they do break them. And they're just constantly moving because they have a lot of kinetic energy being a liquid. But in a solid, they're going to fall into line, right? Or I use another example of like kindergarteners. If there was no, any sort of organization and structure for them, they'd be crazy, like ants running around all over the place. But, if there were structure there, like, no, everybody stands in single file line, don't get out of line. You might not be able to cram as many little kindergartners or whatever into one area. Okay, and even though these bonds are weak, they're not able to be broken unless you add in kinetic energy, which is heat. Surely I'm missing one. Okay, and this isn't perfect, but you get it. They're going to follow or stay within that hydrogen bond formation. There's not enough energy. There's very low temperature, therefore low kinetic energy, and it's going to keep them in place. So you will not be able to have the same amount of water molecules in the space that when it's ice or it's a solid. You won't have the same amount in a certain space as you do in a liquid, because with higher kinetic energy, they can defy those bonds that should be holding them together. Okay, awesome, great.